Hello everyone, welcome to my YouTube channel. So in this lecture, I will teach about the nucleophilic abstraction in hydride, alkyls, and acyl. This is the continuation of this previous lecture, which is on the nucleophilic addition of abstraction in a nucleophilic and electrophilic addition or abstraction about the chemistry. So first, I will discuss about the nucleophilic abstraction in the hydrides. So deprotonation of a metal hydride can produce a nucleophilic metal anion. So for example, like rhenium H7L2 does not lose H2 easily as the L equal to PPH3 complex. To generate the rhenium H5L2 fragment on the DPP case, first the epinephrine and the felkin first form the anion with the butyl lithium and made the intermediate methyl hydride with MEI. The driving force for this methane loss is higher than for the H2 loss, and the required fragment was formed and intercept with the cyclopentadiene to give the unusual polyhydride CP aluminum H2L2. So here, so rhenium H7L2 from to produce the hydride, they lose a hydrogen. It is not a easy because here this phosphine ligand DPP is present in this ligand framework. So for this case, first this metal complex is treated with n butyl lithium. So that produce this abstract a hydride from this metal complex to from this corresponding lithium complex. Then in presence of methyl iodide, upon elimination of lithium iodide, this methyl rhenium H6L2 is from. Then methane is reductive eliminated from this intermediate to from this rhenium H5L2, which is a very unstable intermediate, which is it is very unstable and it will simultaneously as soon as it's formed, it is react with this CP from this CP rhenium H2L2 the final product. So that's why the rhenium hydride is abstracted by the lithium butyl lithium to form this methane molecule to form this final product. So next I will discuss about the alkyl and the acyls. So alkyl group can be exchanged between metals with inversion at carbon. The transmetallation reactive provides a route for racemization of a metal alkyl during the early stages of a oxidative addition reaction, while there is still some low valent metal left in the reaction mixture. So in case for this reaction of Cr3 plus fragment between the metal oxides, the palladium 0 nucleophile to the palladium 2 and reduce the palladium 2 complex to palladium 0. Mechanistic interpretation of this geochemical outcome of an oxidative addition can be enclouded by the exchange reaction such as the one shown. The nucleophilic abstract the acyls of the primary useful in the organic synthesis application as we shall see in chapter 40. So here this metal complex palladium 0 is nucleophilic to palladium. Here it is in the palladium 2 oxidation state, and here is the palladium 0 oxidation state. For palladium 2, here this metal complex is acts as a nucleophile so that attack to the carbon center of this alkyl group and elimination of this metal fragment to form this metal alkyl intermediate. So it is an example of the alkyl group exchange between these two palladium metal complex. So here the inversion of the carbon stereochemistry of the carbon center was altered, so it is in the inverted. So here the inversion of the carbon center occurred. So next acyls are very readily abstracted by nucleophile. As in the abstraction, the reaction goes with the reduction of the metal by 2 units. So palladium 2 acyl is ideal because of palladium 0 state. This is easily accessible. So the recurrence of the palladium 2 in this chapter is no accident. It has a very high tendency to encourage the nucleophilic attack at the ligands and in its complexes. So as an element on the right hand side of the transitional block, it is very electronegativity and its d orbitals are very stable. So here palladium is a encouraged the tendency to nucleophilic attack at the ligand in the complex because it is a very right hand of the transitional block. It is very electronegative and its d orbital are very stable. So this means that the Pauling to the metal electron donation is more important than the metal d pi to Pauling pi star back donation. So the Pauling is left with the net positive charge. So next we will discuss about the electrophilic addition in the organometallic chemistry. So as a zero electron reagent, the electrophile such as a H plus or Me plus can attack the ligand or the metal ligand bonds or the metal even in the 18 electron complex. So particularly in case of proton, the initial attack occur at one side followed by the rearrangement with the transfer of second side. So the location of the electrophile in the final product may be misleading. So electrophilic addition to the metal complexes, they are statistically complex. It is less easily controllable and the less often used for the electrophilic addition. So electrophilic addition. So electrophile is a zero electron reagent. So it can attack either the ligand or the metal ligand bond, or even it can attack the metal. Even the metal is a 8 electron complex. So particularly in case of protons, initially attack may occur at one side, followed by the rearrangement. So electrophilic addition to the metal complex can therefore be mechanistically complex. It is less easily controllable than the electrophilic addition. So addition, the first we will discuss the addition of the electrophile to the metal. So oxidative addition by the SN2 or by the ionic mechanism involves the electrophilic addition to the metal in the first step. So previously we see that the oxidative addition can goes via the SN2 or the ionic mechanism where the net positive or negative charge species generated in the reaction medium. So here this is an example of the electrophilic addition. So here LNM, this MEI is dissociated as a Me plus and I minus. So this Me plus and I minus in the solution. So here Me plus is the electrophile that attack to the metal center, directly attack to the metal center. So from this intermediate, then upon elimination of one ligand L, so the final product is this is formed. So in some cases, second step diagnosis takes place and the counter anion never binds to the metal. So this makes the reaction a electrophilic condition. So here the counter anion, this step I minus is in the counter anion. Here the upon elimination of one L, this counter anion enter to the metal complex. So in many cases, these steps is not favored. It needs not happen. The reaction stop here. So that case, this reaction called is a electrophilic addition. So that this makes the reaction an electrophilic addition rather than the oxidative addition to the metal. Although the latter term is sometimes seen in the literature to describe this type of reaction. So example is the reaction of highly nucleophilic cobalt anion CO TMG pyridine minus with an alkyl triplet, a reaction known as to go with the inversion. Protonation of the metal complex to give the metal hydride also very common. So the Addition of any zero electron ligand to the metal can be regarded as a electrophilic addition. So the ALME3, BF3, HgCl2, Cu plus, even CO2, when it's bind in inter-one fashion via carbon, or can all act in this way. So this is the traditional example of the nucleophilic electrophilic reagents. So it is ALME3, BF3, HgCl2, CO plus, CO2. All are when attacked in an inter-one fashion via the carbon. So each of these reagent has an empty orbital by which it can extract the d type lone pair from the metal. So all of these electrophile are in the electron deficient. So that's they can expect the electron to their vacant orbital of the d orbital, fulfilled d orbital of the metal. So since the extractor atom of this ligand are generally more electronegative than the metal, thus the metal is covalently regarded as being oxidized by 2 units for each zero electron ligand that bind. So that means upon given the electron from the metal to the ligand, the metal is oxidized by 2 units. So metal oxidation increase upon addition of each type of zero electron. This zero electron this ligand. So for example, the Cp2H2 tungsten ALME3 is covalently tungsten is a +6 oxidation complex because the ALME3 is formally removed by closed cell Me3 minus, and the complex formation is of this type is more likely to more basic than the starting complex and a more powerful Lewis acid. So here the ALME3 in this tungsten is in the +6 oxidation state because here for 2 CPU to give each of give -1 negative charge. So there is 2 CP give 2 and 2 hydrogen gives 2 -1. So +4 +4 and here ALME3 is a -2. So one ALME3 is attached, so that will give -2 negative charge. So total +6 oxidation state of this tungsten. So Chung and co-workers show how a conventional deprotonation followed by the nucleophilic attack leaves the metal open to electrophilic attack by the carbonyl carbon in the first step. So here this manganese CO3 plus, here this ring is it is 6% is a nuclear reagent to abstract this hydrogen to form this. Then this to form this intermediate, then this reagent react to form this. The phenyl ring is react here to form this intermediate. Again, the metal this ore is formed. The final product is formed. So next we will discuss the addition of the metal ligand bond. So the protonation reaction are the most common. For example, a hydride can give a dihydrogen complex. So platinum diphosphol 2 is react with this H plus to from this, again this got H plus to from this dihydrogen metal complex. So here is an example of the addition to the metal ligand bond. So all the metal alkyls such as the Cp2, titanium, Me2 are readily reclaimed by the acid to liberate the alkane. A transition alkane complex is more probable intermediate in such cases. The protonation of the alkene complex shown below, it can occur by the two simultaneous paths. One is the direct protonation at the metal and the initial protonation at the alkene, followed by the beta elimination. So this reaction can go via these two possible. One is the direct protonation at the metal center, and another one is the protonation and the at the alkene moiety. Next, beta hydrogenation. So path 2 leads to the conversion of the label from DCl into the alkene layers. So here this metal complex two possible. One is the direct attack at the metal center. So direct upon the metal center to form this metal hydride species, pentagonal bipyramidal species. Next, and another possibility here is hydrogen first attack to this alkene moiety to from this metal alkyl species. Next, the metal elimination to form this metal hydride species. Next, we will discuss about the addition of the ligand. So simple addition to the ligand occurs in the protonation of Cp2N in Cp2Ni as shown by the exoattack by the lack of scrambling of the deuterium level. So here the deuterium is the D plus is electrophile which can attack to the Cp ring on the that is the ligand. So here this exoattack form and this final product is formed. So unlike the nucleophilic case where exoattack is normal rule, for the electrophilic for an endoaddition also possible. As a result, the initial attack of the electrophilic at the metal followed by a transfer to the endophase of the ligand. So this tends to occur where the electrophilic shock like a diazotic exoproton abstraction by OAC can complete the sequence. So that means electronucleophilic case the exoattack is a normal, but endoattack for the electrophilic can also possible. So for this endoattack, the electrophilic electrophile first attack to the metal center, then the transfer to the endophase to the ligand. So this type of metal reaction occur when the soft electrophile like silver acetate. So the exoproton abstraction, we have this exoproton of abstract by the acetate anion to complete this sequence. So for a hard electrophile such as methoxide, CH3CO plus, direct exoattack at the ligand tend to be seen as an acetylation in the of ferrocins. The preferences for an exoproton abstraction means that the exo attack of the electrophile, the endodeuterium has to be transferred to the endo position of the other ring. So these lead to loss. So this is an example of an endo attack. So here the silver acetate is a soft electrophile, so that will first attack to the metal center to form this intermediate. Next, the a transfer to this electrophile in transfer to the ligand from the metal center in an endophase. So finally, the endo product is formed. Next, this acyl acetate anion can abstract this photon to form this final product. So this is case for silver acetate. So next case for this methoxy case, it is a hard electrophile, so it will attack direct to the ligand from the exophase. Next, upon deprotonation to form this inter-ring proton transfer. So exoproton abstraction to form this final product. So that means for hard electrophiles, the methyl jet direct exoattack of the ligand tend to be seen with the acylation of ferrocin. The preference for the exoproton abstraction means that the exoattack of the electrophile, the endodeuterium has to be transferred to the position of the other ring. So this means to loss of the resulting exohydrogen. For this reason, all 5 starting D atom tend to be retained in the complex. The acetyl attacks both ring, but only the result of attack at the C5D5 ring is shown. So next, we discuss about the electrophilic abstraction of the alkyl group. So in electrophilic metal ions, notably Ag plus, mercury plus can cleave transition metal alkyl bonds relatively easily. The two main pathways have been identified. One of these is attack at the alpha carbon of the alkyl, which can lead to the inversion of the configuration at the carbon. In another attack of the metal or the metal C bond, the retention of configuration is found. So electrophilic attack by the metal to the alkyl group can proceed via two pathways. One is direct attack to the alpha carbon of the alkyl group, which lead to the inversion of the configuration or at the carbon center, and next one is the direct occurs attack at the metal or metal C1, which is the result in the retention of the configuration is found. So the difference has been described in the greater basicity of the metal in the iron case. So here this metal complex where this silver, this mercury chloride is attacked directly to the metal carbon bond to form this intermediate. In another case, this is another case. So as a zero electron leader, HgCl2 or modularly HgCl plus can bind to the 18 electron metal exactly in the same way as can a proton. So it is not yet clear whether the electrophilic attack takes place at the MC1 or at the metal. The pathway can give HgCl directly, and the second gives alkyl metal mercury chloride, which can reductively eliminated to give the same product. So in the absence of an isolable intermediate, it is very difficult to tell two paths apart. This is an important process. So as will the electrophilic attack by the Hg2 of the methyl derivative of the coenzyme B12 is the route by which the mercury ion from various sources is converted into toxic methyl mercury cation in a natural water. So here, so first this alkyl metal bond, so it attacks the mercury to form this three-centered three-member green transition state. So upon elimination, this mercury methyl mercury cation is formed. And another possibility we have this direct attack via the metal center to from this intermediate. Next, the chlorine Cl minus attack to form this intermediate, then MCl is reactive eliminated to form this alkyl mercury intermediate. So this is a two possibility for this process. So the proton is often able to cleave the metal alkyls. This happen most readily for the electropositive metals, where the alkyl has a higher negative charge. Even water is a good enough source of protons for RLI, RMGBr, or many of the early metal alkyls. The later metals need to stronger acid and more vigorous condition. So CpL2 FeMe in presence of CF3COH, where the proton abstraction from this acid group to form this cationic intermediate. So upon then this reductive elimination of methane to form this final product. So other electrophils are also shown to abstract the transition metal alkyls as shown below. So here the PH3Cr C plus is an electrophilic that abstract the proton from this of this methyl group to form this intermediate and this PHCME final product. So NO plus also acts as a electrophile that will abstract the proton to form this, and from this to this is formed. So the retention of the configuration is not always observed. The electrophilic abstraction of the vinyl groups, because the electrophilic sometimes gives an initial irreversible addition to the beta carbon. So the free rotation about CC single bond in this carbon intermediate then leads to loss of stereochemistry. So here this is a metal alkene intermediate where the electrophilic attack is the metal carbon metal alkyl bond to form this intermediate. Next, and another possibility also maybe it's attract to the this one to form this, then inversion to form this one, Then from this product is formed. So the halogens are the electrophilic region and can readily clip many metal alkyls to be the free alkyl halides. One common mechanism involves oxidation of the metal. So these increase the electrophilic character of the alkyl group. This degenerate halide ion. So the periodically it is a nucleophilic abstraction of the alkyl group by the halide ion that leads to the final product. So cobalt 3 alkyl are known to here in the same way, and the intermediate cobalt 4, this is stable enough to be prepared by the EPR at minus 50 degrees C. So here this alkyl inversion of the metal center, a carbon center to form this intermediate. Then upon the cerium 4, the oxidation of the cobalt to form this cobalt 4. Then Cl minus is attacked to form this intermediate. So as shown, the more reaction that lead to overall insertion into the MR bond go by the electrophilic abstraction of an alkyl as the first step. So SO2 insertion is the best node, but it is thought that SO3 may be able to react in same way. So an alternative pathway for the reduction of the metal alkyl is the electrophilic is the abstraction of a substituent and the alpha carbon to form this carbene. So here from this alkyl metal alkyl, this electrophilic abstract the photon from the alpha carbon to form this alkene intermediate. Same case, the BF3 is the electrophilic, is electrically deficient to abstract the atom from this metal to from this current intermediate. So next we will discuss about the single electron transfer pathway. So it is sometimes difficult to differentiate between a two electrophilic abstraction and or addition in one step process in which pair of electron is implicated and a two-step process involving a single electron transfer step to a given radical intermediate. So here the LNR electron will abstract the R group to from this vacant site and this ER is formed. So next, so it may be formed via the radical pathway. So for this is a electrophilic, so it will abstract an electron from these two electrons. So from this E radical and this metal positive radical is formed. There is radical abstraction to form this ER and this second electrocatalytic complex. So an analogy ambiguity holds for the nucleophilic reactions. We have already seen on facet of this problem in the oxidative addition of the alkyl halide to the metals, which can go either by the electrophilic addition to the metal and by central process or by the set or the intermediate radical. So the two processes can often give the same product. Other related case we have seen at the promotion of the migratory insertion and the nucleophilic abstraction by the state oxidation of the metals and the electrophilic abstraction of the alkyl group by the halogen. So Hayes and Copper have described the abstraction reaction from a metal alkyne by electrophilic reagent that goes via the set route instead of the normal beta abstraction of a hydride from the ethyl group, which occurs in usual electrophilic abstraction. We see finds a preference of the alpha abstraction from the methyl group since the H atom abstraction usually takes place at the weakest CH bond and the methyl substituent presumably weakens the alpha more than the beta CH of the alkyl. So here the PH3C plus with upon single electron transfer from this constant alkyl group to form this radical intermediate, then the radical abstraction to form this carbene intermediate. Next, the insertion of this carbon intermediate to form this metal alkyl. Next, the beta hydride elimination to form this alkene intermediate and metal hydride bond is formed. So nucleophiles can also give set reaction. Lactin and co-authors have shown that Cp star MoCO3 PME3 plus reacts with the LiLH4 to give the paramagnetic Cp star MoCO3 PME3. So observed by APR, loss of the CO easy in this 19 electron species lead to Cp star MoCO2 PME3, which is abstract H dot, probably from the THF solvent to keep the final product Cp star MO HCO2 PME3. So next, I will discuss about the reaction of the organic free radical with the metal complexes. So reaction of the organic free radical with the metal complex is much less well understood than the attack of the electrophilic and nucleophiles. So if the starting material is an 18 electron complex, the product will be 17 or 19 species and therefore reactive. So the nature of this initial reaction product may be have a interference from the final product. So addition to the metal is well recognized and easiest to detect when the starting complex is 17 electron. So the product becomes 18 electron. For example, organic radicals are known to react very readily with the CO2 DMG2 pyridine as follows. So CO2 DMG2 pyridine at dot at CO3 DMG2 pyridine is formed. So it oxidized this cobalt center to form this cobalt 3 in underscore. So we saw an example of this process as a part of the larger mechanistic scheme in the radical based oxidative addition. We also saw typical radical arrangement used to detect the presence of the metal radical intermediates, since organic radical react rapidly by the pathway shown and only a rapid reaction with the metal complex can be successfully complete. So here this organic radical with recombination to form this alkyl chain or maybe the disproportion to form this alkene or alkyl. So maybe this radical upon to absorb the proton from the solvent to this alkene and solvated radical species. So reaction mean the reaction this reaction means that the solvent also chosen with care or the solvent derived radical may attack the metal complex. So solvent with the strong X-size bond such as water, tert-butyl alcohol, alkane, benzene, acetic acid are resistant to loss of H atom, but the THA, ether or toluene or acetone are much less resistant. So radical abstraction is still uncommon, but is a continuous one step. It has been proposed to explain the acceleration in the rate of the substitution Cp2Ap2CO4 caused by the O2 BET3. In the case of ethyl radicals formed from the BET3 and O2 are thought to be abstract CO from the complex to keep the ETCO dot and the covalently unsaturated 7 electron iron species which undergo substitution. A related radical addition to CO group of iridium ClCO2 PME2 has been proposed by the Bose and Goldman, who generated C6H11 radical by the photolysis of the benzophenone in the cyclohexane and saw CYCHO as an organic solvent. So here the acid PH2CO upon the irradiation to form this activity species with the CYH is abstract. The to form this radical in the CY radical react with the metal complex, this is metal radical, then this metal radical form react with the PH2C dot OH to form this final complex. So Bayard and co-workers has looked at the phenyl azo triphenyl methane as a thermal source of phenyl and triphenyl methyl hysterical that is the compounds of type eta-3-allyl and eta-3-allyl PDP-HCl to give the palladium phenyl compounds. So palladium PHCl to PPS2 and the trans palladium PHCl to PPS2 respectively. The PH3CCH2 all one form and from the triadial abstraction of the allyl cyclohexyl radical from the photolysis and react with the eta-3-allyl PDC to give the cyclohexane and propene. Presumably, no palladium containing products are characterizable. So here this allyl palladium allyl complex conjugate with this radical to form this intermediate. Then the retired elimination to eliminate this alkene moiety to form this metal hydride species. So next this allyl is effectively eliminated to form this dentin. So radical steps are the galvanoxide, tempo, DPPH are the quite sometimes used to test for the presence of radical. Are the solution is such case the radical plungers are expected to the product. So unfortunately, this procedure can be misleading the organometallic chemistry base because the typical scavengers abstract page from some palladium metal at the rate of the competitive with used to typical organometallic reaction. The KD palladium hydride ClPPX also reacts in this way, but the palladium 8 is stable. So in summary, electrophilic and the radical reaction are less easily predictable outcomes than the nucleophilic reaction. So thank you everyone.